Today is lecture 19, Calc 1, Math 141. I do want to make a few comments now that all the tests are graded and have been returned about some kind of generalizations that you, in fact, might have a question for me about as far as how it was graded. I did put on these, everybody should have a solution sheet. Make sure that's the case. If you didn't get a solution sheet, I've got a couple of extras up here. Not that that's the only way to do a problem, because some of you on the parametric equation where you had to eliminate the parameter and write an equation in terms of x and y only, you had a different equation. You went about it slightly differently from the way I did, but yours was still correct. I think some of you actually forgot to do that. You got involved in graphing the parametric equation and giving it a direction, and then what was, I think, a fairly simple part of that problem was to eliminate the parameter, eliminate t, put an equation in terms of x and y. And there's two good versions that you gave on that one. Comments in general. On question 6, which was a limit question, the answer is actually 5/6. Now, if you did the algebra to this, now a couple of you, I think, you compared the degree of the numerator to the degree of the denominator. That's not this kind of limit problem. When would you want to compare the degree of the numerator to the degree of the denominator? When x is approaching infinity. So that is not appropriate for this problem. That's only appropriate for when x is moving way out to the right somewhere. X is approaching infinity. As long as x is not exactly equal to -5, these reduce. And you're left with x over x minus 1. And as x gets very, very close to -5, this numerator becomes very, very close to -5. And this denominator comes very, very close to -5 minus 1, which is 5/6. Now, that's not the end of why I wanted to look at this. Some of you put in values that were very, very close to -5 from both sides of -5. That's completely valid. But you got for your answer 0.83. That's not 5/6. So the limit doesn't approach 0.83. It approaches 5/6. Some of you had 0.833. That is not also 5/6. So it actually goes beyond that. It goes to 0.833 with the 3 repeating. And that's a subtle difference between this answer and 5/6. These are not equal. The limit is 5/6. It's not 0.833. Now, a couple of you put 0.833 repeating. That is 5/6. But 0.833 with the termination of the decimal point there is not 5/6. So the limit is actually 5/6. It converges on that number. It goes beyond this number. It goes beyond this number. 6C, the other limit problem that ends up kind of being stuck with division by 0, and we can't avoid it. There's no way to reduce that bad factor of x minus 3. There's nothing in the numerator that allows us to reduce it, so we're kind of stuck with division by 0. A couple of you had negative infinity, and at least one person had positive infinity. the correct answer is does not exist, but is it really either one of these? This function right here has a vertical asymptote at 3. And on one side of 3, let's just see if we put in a value larger than 3, what do we get? Positive, positive, positive. Is that right? If you put in a value larger than 3. So it comes in from this side toward positive infinity. If you put in a number smaller than 3, that's positive, and that's negative, so it does this. So is either one of these answers correct? Not by itself, because on one side it's going to positive infinity, on the other side it's going to negative infinity, so it's not really one or the other, and because it's both, it's technically not either. So this is really the only answer to that problem. It's positive infinity on one side, negative infinity on the other, so you really can't isolate either one of those answers. Probably the most frequently missed were the problem 7 parts where you're given a parabola in kind of general form and asked to put it in standard form. There were some creative ways of getting that thing graphed, which were pretty clever, and they worked, and you got either most of the points or all of the points. But 7a was a parabola, and 7b was a circle, and I've detailed both of those kind of completing the square methods that show that that was a circle with certain center and a certain radius. One more thing. Question 8. Average velocity. This is a pretty critical idea as we move on through this material in Chapter 3. Average velocity. So the unit length is feet. The unit time is seconds. So we want a velocity. We want our final answer to be feet per second. So another way to think about that is we want basically the slope of the secant. We want to connect 2 points, and we want to know the slope of that. So we've got this S of t curve, which is negative 16t squared plus 64t plus 100. Negative 16t squared, we saw that as the gravity part. 64t, we saw that as the initial velocity part. And plus 100, we saw that in previous problems as the initial position. So here's a sketch of what this thing does. It starts here at 100. At time 0, that's its position. We want to know during the first 2 seconds. Well, if we want average velocity, we need the position at time 2 minus the position at time 0. What is the position or height? What unit is that? That's feet divided by 2 minus 0. That's time. Time 2 minus time 0. That unit is what? Seconds. There's your velocity. Now, some of you took velocities in the numerator. Well, what unit are velocities? They're feet per second, and then you divided them by seconds. What do you get when you take feet per second and divide it by second? You get an acceleration. That's no longer an average velocity. That's an acceleration. Feet per second per second. So you want position at time 2 minus position at 0 over the difference in the times 2 minus 0. And that gives you the unit. So a lot of times if you're not sure in a problem kind of what to do, then pay attention to the units and work from the units back to what might get you those units. We want difference in height or difference in position over difference in time. And that's an average. So it kind of gives us, let's see, where is it at position 2, 164 feet? So it gives us the slope of this secant line. Slope of the secant is still a velocity. It's not slope of the tangent, but it's average velocity. I think that's the only thing that I needed to comment on in general about that test. Anything from what we did yesterday in 3.1 with kind of our first round with the shortcuts on the derivative?
I have another question on 2.8. It's from
Okay.
Levisign.
All right.
There's a picture of a graph, so, and it's the, do you want to look at the graph?
Yes. I should bring that with me, but I don't.
I have it here.
Does anybody have WebAssign
Right.
2.8 with them? Here. Can you get that, Calissa?
That's the picture of the graph.
Okay, and that's F prime.
Yes.
All right?
I think so.
Yeah. But it says Y equals F
Okay,
prime.
yeah.
So we'll use, and because I have asked a question similar to this, I'll put this one on here. So it looks like it's here. Zero here.
Which question is it? It's number 1 on 2.8.
The one about
Oh, wait. Oh, no, I can't.
4, it's up here. 5, it's here. And 6, it is down here. All right, so we have a curve that looks something like this. I can't read the directions.
Here,
Thank you.
oh.
But this y value is not y like f of x. This y value is the f prime of x. So this is a graph of the derivative.
F of x, or I'm sorry, A is actually asking on what interval is f increasing.
Okay. So we want to know when is f of x increasing. All right, let's answer that. How many pieces are there to this question? Just 2 parts?
Yeah, there's 2 parts.
Okay. So let's get this one.
Oh, I'm sorry, there's a lot of parts.
A lot of parts.
Yeah.
Okay. So remember, this graph is f prime. And the question we're trying to answer is when is f increasing? So what do we want to pick off of this graph to answer this question? When it's positive. When the derivative is positive, that means that the function is increasing. So we wouldn't need to know when it's positive. So these are, I hope I've got these units right.
Yeah, you do.
So these are single
Yeah.
units across here.
Yeah.
We don't really need y values. We just need to know when the y value is above the axis and when it's below the axis. For right now, we need to know when the y value on the derivative graph is positive. So that is what, 0 to 1? It's not really positive at 1, is it? It's 0. So this one, right?
Yeah.
And then it's negative again for a while, and it looks like we pick up at 3, but not really at 3 because it's 0 at 3. And then these values are all positive, 3 to 4, up to, but not including 5. Does that work?
Yeah.
And then it's negative again from 5 to 6. So here is where the y values on the derivative graph are positive, which means that the other function, the f of x function, would be increasing. Does that answer that one okay?
Yeah, so decreasing would just be everything negative, right?
Where the y values on the derivative graph are negative.
And it says at what values of x, b is at what values of x does f have a local maximum? It
Okay.
has local maximum. And
All right, so we're not, B is,
Oh,
you're okay
no,
with
B
B?
is the
Everybody
second.
okay with B?
Yeah.
Where is it decreasing? Where the derivative is negative? Okay, and the next question is, where does it have a local max? Think about what, for f of x to have a relative max. Here's an f of x picture. Wouldn't it have to be what? Increasing, and then flat, and then decreasing. Is that right? So increasing back on this graph means what?
0.
Positive,
Oh.
right? Derivative is positive, means the function is increasing. So we need a graph that is positive, and then slope is positive, slope is 0, and then slope is negative. Is here positive, 0, negative?
Yes. Yep.
Okay, so should we have a relative max at x equals 1?
Yes.
Is that correct? And we don't know the y value because, and I hopefully it doesn't ask you for that. It just says what is the x value, right, where a local max is located. So whenever the derivative graph goes from positive to 0 to negative, that creates positively sloped, 0 slope, negative slope. It's got to be a relative max. Now, where else does that happen? 5 goes from positive to 0 to negative, right? Slope. So that means that x equals 5. We've got a relative max as well.
And then relative min would be the 3, right?
Relative min, we would want it to decrease, then be flat, then increase, right?
Uh-huh.
So negatively sloped, 0 sloped, positive slope. So negative to positive, where's that, 3?
3. Yeah.
We're negative, 0 at 3, and then positive. So relative min at x equals 3. Where else does that happen?
That's it.
That's it, right? Where it goes from negative to 0 to positive. So that's our only potential relative min. Is that it for those questions?
Mm-hmm.
Anything else? Homework? Something in the book that needs to be clarified? Where do you think that I got the questions about putting the parabola in standard form and identifying stuff and graphing it, and putting the circle in standard form and identifying center and radius and graphing that? Where do you think I found those? They're in your book. You'd be surprised how many questions that I'll get, not only from WebAssign, but just problem, and WebAssign problems are also from your book, most of them. So make sure that you're not just, depending on what we do in the classroom setting, that you're digging into the book and looking at some problems. I'm not saying all of them, but sample some problems and also do the same thing with WebAssign. I don't know if I recommended how to do WebAssign, but if I were doing WebAssign, I would download it, actually print it, start to work on it so I have a record of my work, and then if something was successful, I've got my work written down. I know what worked, and if it wasn't, then I'll do another sheet of paper until I get it right. That's the nice thing about WebAssign, is you get to work to perfection if you want to take the time to do that. And then you have a record. You can go back, and when you study for the test, you can look at the work you did on solving the WebAssign problems. Otherwise, I don't think just doing them is valuable, but doing them in a manner that you have a record to look back on is way more valuable than just doing them. Kind of in a little bit of a scolding mood today. Does it sound like that? Don't take me wrong here. I don't enjoy making a bunch of red marks on people's tests. I would rather not make a mark at all, or maybe a big old red smiley face or something. I mean, or just nothing. So I didn't take joy in giving some of those grades, because what it does is it says to me that I didn't do my job very well. I mean, I'll take my share of the blame as long as you're going to be willing to take some of your share of the blame too. But that doesn't make me happy to mark a bunch of things wrong on a test. I'd much rather make very, very few marks. So let's see if before we take a test again, I can connect a little better. All right, let me try this smart board behind me. See if I can master a new form of technology. Bear with me, because I've practiced very little on this. We are going to finish 3.1, so we have started derivatives by the shortcut. So our function today is a to the x. So if we have a function a to the x where a is a number, 2 to the x, 3 to the x, and eventually, before the class is over today, I'd like for us to get e to the x, which is a number between 2 and 3. So we're talking about y equals 2 to the x, y equals 3 to the x, and then eventually y equals e to the x. So that's kind of the goal. But if we do this in a generic sense, with it being 2 or 3 or e or 10 or any other number, we can establish a process that we can shortcut this when it's all said and done. So if we want f prime, we don't really have a shortcut for that yet. So anytime we are developing our own shortcut, we have to go back to the definition. So the limit as h approaches 0, we want this function. Let me see if this works, if I can use my finger. Yes, I can. So it's magic. That's why they call it what it is. It's a smart board, a lot smarter than I am. So we want that function at x plus h minus the function at x all over h as h approaches 0. Got a little clutter there. Let me see if I can get rid of some of this. Everybody agree? Definition of derivative on this function. F of x plus h minus f of x all over h as h approaches 0. So we have to go backward a little bit algebraically. A to the x plus h, is that the same thing as a to the x times a to the h? Probably you haven't done it in that direction before, but certainly if you have the product of two things with like bases, you can add their exponents. So it ought to work the other direction. So I want to write this one, a to the x times a to the h. Do you see any advantage to doing that? Okay, we do have an a to the x here, and we have an a to the x here, so we can factor that out in front. All right, let me see if I can get a... I need a new sheet. See, I told you this thing was a whole lot smarter than I am.
Hit the red X.
Well, this one?
Yes. Put the pen down first.
There we go. Oh, it was. That's why. That's why. Thank you. All right. Told you I'm learning here. So we want. Whoa. What happened there?
It should reset. Just put it down and pick it back up.
Okay. Put the pen down. Okay. There we go. So I have to go when I see the green light. Is that correct?
Right.
Okay. So we want f prime. Told you there'd be a little bit of a learning curve here. All right, so back on the prior screen, we had an a to the x. In both terms of the numerator. So we'll factor out a to the x. The nice thing about having factored that out is that a to the x is unaffected by h approaching 0. So we could, in fact, just bring this piece out in front. Doesn't change. There's no h in it at all. Now, obviously, the rest of this is going to change as a changes. So if a is the number 2, then we'll get a certain value out of this as h approaches 0. So if a were equal to 2, somebody on your calculator put a 2 in here. Put 2 to the some value that approaches 0. Subtract 1 from that, and then divide it by that same h value. .693.
Maybe not.
I think that number's actually come up in this class before. The .693 number. Somebody that has your calculator out and working, punch in the natural log of 2. See what you get. .693. So when we put in 2 and do this particular limit problem out here to the right, this piece right here, when you plug in 2, you get this value, .693. .693 is an approximation for the natural log of 2. Now I want. So we've got this derivative when a was equal to 2. It ends up being a to the x. Well, a is 2, so it's 2 to the x times this decimal stuff, which turned out to be the natural log of 2. What happens when a is 3? Well, we need the limit of 3 to the h minus 1 all over h as h approaches 0. So let's pick a value very, very close to 0. Somebody run that through your machine and see what you get for that limit. 1.09. What might you guess that number is? Natural log of 3. And if that, you need to validate that, punch that into your calculator, and check out the natural log of 3. So when a is equal to 3, the derivative would be 3 to the x. Generically, it was a to the x times this other decimal stuff, which turns out to be, in this case, the natural log of 3. So in general, if our function is a, where a is a value that is positive and is not 1, then the derivative is itself. That seems a little bit awkward because we think the derivative is going to knock something down a little bit, like the derivative of x cubed has an x squared in it. Derivative of x squared has an x in it because we're used to that kind of knocking down. This is exactly the same thing, actually, with a little bit of extra baggage. So the derivative of a to the x is itself a to the x, the extra baggage being the natural log of a. So let's suppose the original function is e to the x. E is a number. It's not as nice as 2 or 3, but it's a number between 2 and 3, approximately 2.718. Rears its head in mathematics a lot, this number e. The natural exponential function, the natural logarithmic function, comes into play a lot in mathematics. this is still the same kind of deal. This is still a to the x, right? A is a specific number. It sounds like another letter, but it isn't a variable at all. It's a number, e. So the derivative should work the same way. So if that is the case, what should the derivative of e to the x be?
E to the x.
Times
Natural log.
e to the x times the natural log of e. Good. Natural log of e is 1. That's the nice thing about this one. When we use 3, 3 is a little more than e, and we got that number, what, 1.0986, something like that, for that extra baggage. Well, when you're dealing with the number e, the natural log of e is 1. And if you need to justify that, when you're trying to find the natural log of something, it's the power that you would raise e to get that something. What power would you raise e to get e? You'd raise it to the 1. You'd raise e to the 1 to get e. So that means that the derivative of e to the x is e to the x. I remember the first time I saw that, I didn't like that at all. I didn't like the fact that the derivative of something was the exact same thing as the original function. So let me show you what that means graphically right here. I'm going to switch horses, Leonard. Is that a problem? I guess not. So here's what that means graphically. So we're going to graph e to the x. And we just decided that its derivative is also e to the x. So if we were graphing it at, and I'll need some calculator help here, if we're graphing this at -2, what is e to the -2? 0.137? Probably a lot closer to the axis than that. When e is -1, what's e to the negative first? Okay, about a third, a little bit more than a third. E to the 0, I'll do my part, that would be 1. E to the 1, e to the first ought to be just e, 2.71. And e to the second. 7.39. So one thing about the graph of e to the x, once it gets going, it goes up in a hurry. So this point, -2, somebody tell me what that decimal was again? 1.135. And -1 was point. Now the reason I want to write down the y value, let me write them down and then we'll talk about the reason why we want to pay attention to the y value. 1 was
1
that, and 2 was 7.389. So if we take these points which are on this graph, y equals e to the x. By the way, isn't this graph always increasing from left to right?
Yes.
So if the graph is always increasing, the derivative should be positive in all cases. So wasn't the y value e to the x? Is that true?
Yes.
And we're also saying that the slope at that point is the same as the y value. Is that correct? So let's pick the easiest point right here. What should the slope of this tangent line be at this point? The slope should be the same as the y value, which is 1. Is that correct? I hope the graph kind of looks like that. I hope that line looks like it has slope 1. If we come out here to this point where x is 1, what should the slope of that tangent line be when x is 1? It ought to be the same as the y value. The slope is the same as the y value. The y value is e to the x. The slope is e to the x. That tells me that the slope and the y value are the same. So the slope here is 2.718. So this is a very unique curve in mathematics where the slope of the tangent line is exactly the same as the y value that you plotted. That's what this says. Look at the y value, you know the slope of the curve. This point right here, what's the slope? The slope is the y value. The slope is 0.135. What's the slope here? 0.368. What's the slope here? It looks pretty steep. That slope actually is 7.389, roughly. That's an approximation. In fact, all these are approximations except for 1, right? That's exactly 1. So that is a very unique curve such that its derivative is the same as the original curve. Yes?
Would e to the negative x be the same?
A little bit of extra baggage because of the negative x. It actually, e to the negative x, you can probably figure out what the extra baggage is. I'm going to move this sheet. Any issues on this before I move it? To answer that, try to answer that question. So e to the negative x, doesn't it look like this? Is that correct?
Yeah.
Now, what should be the slope of every line that's tangent to this curve? Better be negative because this curve is decreasing. So this original function is e to the negative x. The question is, should we expect the derivative to also be e to the negative x? Well, e to any power is always a positive number, right? So this is positive. So any guesses about the extra baggage that we would need to bring along? Negative. All you have to do is negate it. Okay? And that involves something that we're not quite ready for yet. It involves actually the chain rule. Because we don't just have e to the x, we have e to some, even though it's a simple function of x, but it's e to a function of x. But this won't work. What will work is negative 1 times that, because we want the slope, we need for the slope to be negative. If this is true, and I need some validation here, remember what we did to get this. We took, so f of x is e to the x. We've done this in general with a. Now I'm just putting in a specific number, e. So that's e to the x times e to the h. We factor out an e to the x. If we want our final answer to be e to the x, which it is, so this is going to be the final answer, what is that? That better be 1, right? Somebody try that on your calculator. Try e to some tremendously small value. Subtract 1 from it. Divide by that tremendously small value. Do you get something very, very, very close to 1? And if probably of what, 3 or 4 or 5 decimal places? Okay. So this, in fact, is 1 when the base of our exponential function is the number e. So the derivative of e to the x has been validated a couple different ways as itself, e to the x. So the slope of the tangent line is the y value. Now, what does that give us? What do we have enough information, enough ammunition to do at this point in time? we have functions that are polynomials. We can find their derivatives. So we can do any polynomial function. In fact, not only can we find the derivative, we did an application problem yesterday where we set the derivative equal to 0, right, to find the places where the tangent line was horizontal. So we can actually do a kind of a low-level application problem with a polynomial function. We also, if we start with a function that is an algebraic function like square root of x, x to the 2/3, we should be able to x to the negative 2/3, x to the 4/5, anything like that, we can use that same power rule, right? We have the ammunition to find those derivatives. And I want to finish up class today with one pretty simple looking example like that. And what we just covered then is that we have the ability to differentiate e to the x. Certainly, it is its own derivative. When we do antiderivatives, by the way, this will be the one that will probably be the first one we gravitate to, because if the function is its own derivative, won't it be its own antiderivative? It ought to be the same, go in both directions. Now, we're really not going to use this so much right now. A to the x, where a is any other number other than 1. But when it comes to the point in time where we do need that, we have that as a to the x with that little extra baggage of the natural log of a. So here's a simple function that I want us to finish with because I know what happens at a certain point, and it shows you how simple a function can be and for there to be some issues with that function. Cube root of x. Not bad. We could say that's x to the 1/3. And that would probably be the way I would want to look at it before I took its derivative. What's the derivative of x to the 1/3? Good. 1/3 x to the negative 2/3. So I want the cube root of x, and then I want to square it. It doesn't matter when you take the cube root and when you square it, as long as you do both of those things. Now, you might say this doesn't give you any information, but in fact it does. Could this derivative, could this fraction ever be 0? Never is 0. What makes a fraction 0? 0 on the top. And you're never going to get 0 on the top. There's no variable on the top. So this thing is never 0. You might say, well, we kind of struck out there. It didn't give us any information. No, we do know something about this graph. If the derivative is never 0, we never have any of those relative max or relative min kind of points. We never have any flat points, right? So this graph is never flat, so to speak. So seemingly gives you no information, but in fact it does give you some information. And this is relatively new, so this is the reason why I wanted to do this one. Is it ever undefined? Is this derivative ever undefined? Is this framed quantity ever undefined? It is, when x is 0, right? Now, can x be 0 in the original function? Is there such a thing as the cube root of 0? Yeah, 0. So this is a nice continuous curve. But the derivative is undefined when x is 0. Think of an undefined slope. What visual image does that conjure up? Undefined slope. Vertical, right? So if you were to plot points on this graph, which, by the way, when you put in 0 into this original function, you get 0, right? Cube root of 0 is 0. That is a point on this graph. What is happening at that point? There is a vertical tangent line there. So I'll just put in a little, it's not an asymptote, that's just kind of a little guide. You would see that if you plotted more points, this gets more and more vertical, very steep right here as it comes into this point, and it leaves here very steep as well. So that's what the graph of this looks like. Is the graph ever flat? No, it never is flat, and we knew that was going to be the case. And is it ever ridiculously steep to the point where it's instantaneously vertical? Yes, right here. But it is continuous. So even a simple function like cube root of x, the derivative can fail to exist, and then we can interpret that graphically as a vertical tangent line. When x is equal to 0. All right, we're finished. Thank you for your attention.